20b is about two main concepts. The first is rewriting vectors in column form in a form called component form. It's also about how we find the length of vectors. So with vectors, we can denote the column vector 1, 0, or moving 1 unit to the right. We can call this vector I. We can also call a vector 0, 1, where we're moving one component up, as vector j. Hence, we can rewrite any vector in component form, which is basically writing it in terms of I and j. So if we have column vector a1, a2 as shown, we can actually write this as a1i, and you can think of I really as the x direction, and we can add on then a2, or our second column component, j, where j is really movement in the y direction. Notice here that I in this case is not the square root of -1, it just represents this column vector shown above, the same with j. So if we have vector u, and that's equal to the column vector 7 minus 5, we can write this as 7i minus 5j, because that would be 7 times the vector 1, 0, minus 5 times the vector 0, 1. So you have 7 units in the x direction and minus 5 units in the y direction. They're just two different ways of writing the vector u. The modulus of a vector refers to its magnitude or length. So if again we have this vector a1, a2, or a1i plus a2j, the same thing, we can find the length of the vector by taking the square root of our first component squared plus the second component squared. Regardless of which way you write the vector in column form or component form, we do the same thing. Do not include the I or j underneath your square roots. It won't make sense. For instance, for our vector 7 minus 5, we can find the length by taking the square root of 7 squared plus minus 5 squared, and we'll get 2 root 19. That means for our vector u, I know its length from the origin to its final point is 2 root 19 units long. Sometimes we denote the length by two absolute value signs around our vector. Okay, so we know our two concepts. Let's look at some examples. The first one is in two dimensionals. If we have a vector a equals 5i plus 2j and b equals 3i minus 2j. Firstly, I want to write a plus 2 times vector b in both component form and as a column vector. I'm going to show you two ways of doing this. The first way is using the component form, and the second way is going to be using column vectors. So the way we do it in component form is we just add the I components together and the j components together. We expand as usual. So do the 2 times vector 3i minus 2j. That will give you 6i. 2 times minus 2 is minus 4j. Then we add 5i plus 6i. We'll get 11i. And 2j minus 4j, well, that is just minus 2j. So it's a lot like algebra in this sense. Follows the same rules. The other way you can do this is using column vectors. So convert both vector a and b into column vectors. A would just be 5, 2, and b would just be 3 minus 2. Put this in equation, so we have a plus 2 times b, and you know how to do this. First, do the multiplication of the 2, so 2 times 3 is 6, 2 times minus 2 is minus 4. Then combine these into one vector and add the components. 5 plus 6 is 11, and 2 minus 4 is minus 2. Notice that these are the same answers. We get the same vector, just in component and column form like us. The next question says compute -6 times A. Again, in component form, we can just write it out and expand through. So we'll have -6 times vector 5i plus 2j. -6 times 5 is -30i. -6 times +2, that's -12j. Alternatively, you can do it in column form. But just remember that you should write it in the form that was given to you in the question, unless specified to do otherwise. Both of these vectors represent a vector that moves 30 units to the left and 12 units down. Lastly, we have to find the modulus of vector B as well as vector 2b. This just means find the length of these vectors. So sometimes, remember the notation, have your two lines either side of your vector. That is called the modulus or the length. That's how we denote it. And then we take the square root of our first component, 3 squared plus -2 squared. So we'll have the square root of 9 plus 4, and we can simplify that to the square root of 13. So that's the length of vector B. Again, you can write this in column form and just square your two components and add them together, then take the square root. We also need to find the length of 2b. But remember, if you times a vector by 2, you are doubling the length. So all I have to do is double the length of b, which we know was 13. So the length of vector 2 times b is 2 times root 13. What about if we look at this in 3 dimensions? Example 2. If A is the column vector 5, 6, and 7, your first question is, how do I write this in component form? Now, we need to remember that the first component represents our x direction or our I direction. The second component is our y or our j direction, and our third component is our z, or, you guessed it, it's called the k component in component form. So we can actually write A, or vector A, as equal to 5i plus 6j plus 7k. So the third component is denoted with a k, or k is equal to 0, 0, 1 in component form for 3D vectors. Part B is to sketch it. So I'm just going to draw up our plane with my I, j, and my k, or my x, y, and z axes, whichever way you would like to think about it. This vector goes 5 in the positive x direction. It goes 6 in the positive y direction, and 7 up on our z axis. Okay, we're starting at the origin and going to this point, 5, 6, 7, and this is my vector A. We end up in this front quadrant where everything is positive. Now we need to find -7 times vector A in component form. So I'm going to multiply this out in component form. I'll have -7 times 5, which is -35. Keep the I there. -7 times positive 6j is -42j, and -7 times 7k would be -49k's. Just multiply the number through. Now we're going to find the length of A and the length of -7a. All we do is the same thing. We square and sum all of the components and take the square root. So we'll have the square root of 5 squared plus 6 squared plus 7 squared. That will be the square root of 25 plus 36 plus 49, and we'll end up with something like the square root of 110 units. Now, I've already computed what minus 7 times vector A is, so I'm just going to square the components of this. Of course, you could just instead times the length of A by 7. The direction wouldn't matter here. You should still get the same answer if you use that method. But if I do it this way and I get the square root of minus 35 squared plus minus 42 all squared plus minus 49 all squared, take the square root, I get the square root of 5,390, and that's approximately 73.416 units long.